Let's solve another problem, this one involving liquid water flowing through a variable area duct. Liquid water flows isothermally at 20 degrees C through a one inlet, one exit duct operating at steady state. The duct's inlet and exit diameters are 0.02 meters and 0.04 meters respectively. At the inlet, the velocity is 40 meters per second and the pressure is 1 bar. At the exit, determine the mass flow rate in kilograms per second and the velocity in meters per second. Well, let's model this system. We'll start with a schematic. We have an expanding duct where the diameter doubles over some distance, and we have liquid water flowing through it. What we're given about this problem is we know the inlet diameter, we know the velocity at the inlet is 40 meters per second. We know at the inlet the pressure is 1 bar and the temperature is 20 degrees C. We also know the diameter at the exit is twice the diameter as at the inlet. And this is an isothermal flow, so that means the temperature at state 2 is the same as the temperature at state 1. We're going to model this as an open system operating at steady state, and I'm assuming that this is subcooled water. So anytime we're dealing with liquid water, such as what comes out of our faucet, that is subcooled water. We want to find the mass flow rate at the exit and the velocity at the exit. How are we going to do this? Well, we said the liquid water is subcooled at 20 degrees C, and it's the same temperature at the inlet and the exit. So it's going to be subcooled at the exit too. And also the specific volume at the exit will be the same as the specific volume at the inlet. And we can find a specific volume for subcooled liquids. V1 is going to be V2. And that's just approximately equal, although it's very, very, very close to the specific volume of a saturated liquid at 20 degrees C. And from our saturation water table at 20 degrees C, we get a specific volume of 0.0010018 cubic meters per kilogram. So now let's calculate the mass flow. It's area times velocity over specific volume. And since we know the velocity at the inlet, let's solve for the mass flow rate at the inlet. So it's the inlet area, which is pi over 4 times 0.02 meters squared, times the inlet velocity, 40 meters per second, divided by the inlet specific volume. And we get a mass flow rate of 12.54 kilograms per second. But we know that the mass flow rate of a single inlet, single exit piece of hardware is the same at the inlet as at the exit. So now let's calculate the velocity at state 2. So at the exit of this duct, the velocity is given by the mass flow rate times the specific volume divided by the area. We just calculated the mass flow rate at the exit. We know that the specific volume at the exit is the same as at the inlet, being an incompressible subcooled liquid. And we can calculate the area at the exit as pi over 4 times 0.04 meters squared. And we calculate a velocity at state 2 of 10 meters per second. Now there's an alternate solution to this. We can use the inlet outlet ratios. So we know that area times velocity over specific volume is constant. So AV over specific volume at state 1 is equal to AV over specific volume at state 2. But we know the specific volumes are identical. So now we're just left with area times velocity is constant. We can rearrange and solve for the velocity. It's just A1 over A2 times the initial velocity. Well, the area state 1 is pi over 4 d squared, d1 squared. And the area at the exit is pi over 4 d2 squared. Pi over 4's cancel. And we multiply times the initial velocity, and we end up with the same velocity at the exit. It's 10 meters per second.